Okay, fine. As I told you in the morning session, we will start with the simple lab document. So just once again, what I will do is I will upload the notebook. So while I select this notebook first, right? Very easy K-means implementation, IPython notebook. So I request all the participants to select this notebook first to better understand how K-means can be implemented in Python. So then we will see the what is a mechanical engineering scenario for which K-means can be implemented, right? So first we will select this very easy K-means. So I think all the participants are with me. Any doubts, please let me know. So if all the participants have up- what to say uploaded this Python notebook, please let me know in the chat box. Are the participants able to listen my voice? Hello, sir. Fine.
It is clear, sir. It is clear.
Yeah. Okay. Okay. Thank you. So, yes, we are here now. You see what we have imported, what packages we have imported to perform K-means clustering. So the first package that we have imported is sklearn, and in this package we are using submodule called cluster, right? So this sklearn, in the sklearn package we have used cluster submodule, and in that cluster submodule we have a Python class by the name k-means, right? So we are we are importing this k-means Python class in order to perform k-means clustering, right? So in order to see the elbow where it has actually bent to see SSE value drastically coming down. So what we are doing is we are using simple matplotlib Python package in order to plot the elbow method, right? So now what we are doing is we are defining two feature data, right? We have two-dimensional data x and y. So what we are doing is we are creating it as a list, right? We are creating it as a list and we are assigning into data variable, right? So now this list is shown like this. You see the first value of x and the first value of y has become a pair here. Why? This is because of making it as a list and you are using zip method to group them, right? So 4 comma 21, 5 comma 19, 10 comma 24 and so on, right? So like this, what happened, you have generated your data points. uh, we are in the morning session we have seen the numerical example where we have considered two-dimensional data, and by using the two-dimensional data we formed clusters, right? We formed clusters. And now what we are doing is initially the SSC value is 0, right? Inertias are nothing but SSC values here, and this value is 0, right? Now what we are doing is how many values. So I request the participants to mute their mic. Thank you. Fine. Initially the inertia value is 0, and we would like to know how many data points are there: 1 2 3 4 5 6 7 8 9 10. So we have 10 data points, right? What we are doing is in the range 1 to 11, so it could be any value, right? The number of clusters you can specify in between 1 to 11, any value, right? You are calling k-means method, and you are supplying the parameters number of clusters. So as you know, k-means algorithm requires prior information in terms of number of clusters. You are passing that prior information, right? Now you are using a variable called k-means to hold that result, right? So this k-means, on the k-means variable, you are calling the method called fit. So this fit, what it does is it forms clusters, right? It forms clusters and calculates what is called as and it also provides what is called as inertias, right? The algorithm, what it does is it fits the, it warms clusters and also and also generate inertia values, right? So in order to find out these inertia values, you can print those inertias, right? After this after this for loop, you can print the inertias. So now, but for now, what we are doing is we are simply showing the marker here. You see, we are plotting the elbow method, right? And this elbow method, what it is doing, we are calling the method called plot. This plot generates what is called as line plot, right? It generates line plot. And what you are specifying, you would like to have inertias as y-axis data, and a range of values which are nothing but your number of clusters in this loop, right? From in between 1 to 11 as x-axis. So x-axis values, y-axis values, and you would like to use the marker symbol as this such, right? This one. So you are specifying the title of the plot as elbow method, and x label to be number of clusters, and y label to be inertia, and you would like to visualize that plot. So when you run this, we should be able to see, right, the elbow method output. So if you run this, what is the problem? We name k means is not defined, so we need to import the package, right? We are importing the package and we are running this. Now you see the plot. So we have got the plot. So if you see this plot at the value k equal to 2, the elbow has been bent, right? There is a clear understanding that this particular line plot has bent at k equal to 2. So the number of clusters is now 2, right? So as we have found that at the k equal to 2, the elbow has been bent clearly, we finalize upon the number of clusters as 2, right? Now what we are doing, now we are simply specifying the number of clusters to be 2, and we are fitting the data to generate partitions, two clusters, right? So upon calling fit of data, what it does is it generates two partitions, and we would like to see the partitions in the form of a plot. So what we are doing is we are calling scatter method to see the plot, right? Partitions of clusters, group of clusters. So we are using scatter plot, and we are passing x comma y values, and we are also specifying this label. So k means itself has got so many things. So if I simply type k means dot, right? K means dot. So how many things are there with k means, you see? So we have fit method, we have fit predict method, we have fit transform method, get params method. So if I call this get params method, so what happens, you see, right? As I would like to print, better to print that message, right? Print. So, so these are the parameters. You see, algorithm Lloyd copy underscore x. Uh, so algorithm used is Lloyd and copy underscore x is true. The initialization is with k means plus plus. Maximum iterations are 300. So 300 iterations, the maximum number of iterations considered is 300. So and the number of clusters to be formed is 2. For forming two clusters, uh, it does not go till 300 iterations. Within very less number of iterations only, the two partitions will be generated, right? And random state is none, and a number and initialization is warning, and so on, right? So verbose is 0 doesn't mean there is no description here. So if I simply change the verbose value as 1, right? K means dot verbose. Mm, so if I see K means dot, we have verbose, verbose, whose value is 1, is equal to 1. If I say 1, what happens, we'll see, right? Expression cannot assign assignment, which perhaps you meant double equal to. So if I say double equal to, do we have any verbose information? False. So there is no verbose, no description specifically, right? So no need to have, there is no description for this. That is what it means, right? So finally, what we have done, we have seen two clusters getting generated here, right? So any doubts with respect to this? It's a very simple example that we have taken. Yes, any doubts? Yes, participants, if you have any doubts, you can type it in the chat box, or you can unmute yourself and ask the question.
Sir, you can continue, sir.
Fine. Okay, sir. Then I will, with this simple demonstration, what we do is we will quickly go to the ME scenario, right? Upload notebook. So we take the today the ME scenario that we have discovered in we have discussed in the morning session. So that is quality control in manufacturing, right? So Python notebook I am simply uploading here. So now see here, what we are doing is we are importing k-means class once again, because we are working with k-means, and we are importing matplotlib to show the, what you say, plots like elbow method, and we have used they say components, principal components. So you see, and we have also used numpy and pandas to hold the data and to manipulate the numerical data. And we are using a standard scalar class to convert the data into zeros and ones, right? To convert the data into zeros and ones whenever there is a sparsity identified in a particular column. To convert that values into zeros and ones, we are using pre-processing standard scalar class. And under decomposition submodule, we have a class called PCA. So we are using this PCA class to show the principal components also, right? So here we are generating a synthetic data on number of samples to be 300 with the features for which means we have 4 attributes and 300 instances, data instances, so 300 rows in the data set, right? With 4 attributes and 300 rows, we are generating a synthetic data. And this synthetic data is not real manufacturing data, right? Just for the sake of demonstration, we are generating this. And now what we are doing is we are generating that data in the form of pairs, right? In samples and in features, right? And now what we are doing is we are multiplying that value in 10 into 10. So this means what do you mean by this? You are increasing the size of the data 10 times, right? So you're increasing the size of the data that 10 times. That's why you have seen when you plot the data in the Excel, right? You have seen the points in that fashion, right? If there were 300 samples, you might not have seen those many number of points in the today's in the morning session presentation. but we are multiplying the data 10 times. So that's why we have seen those many number of points, right? And now what we are doing is, yesterday this was the point we have missed, right? In the when you are saving to file into in the CSV format, you will also specify what is the separator for CSV is comma. Because it is comma separated values, you are using comma to separate, right? Then you are converting the data into zeros and ones, and this data, what you are doing is, you are using this data. This data contains four features. Actually, there is no need to convert this data into principal components, because the number of features are only four, right? So, but the most important point that you need to consider is why we are using PCA here is, when you are uh, when you are increasing the size in 10 times, you are also including the number of features. So that means initially the number of features are 4. Now after multiplying by 10 times, the number of features have been increased to 40. So because of this, we are going to reduce the dimensionality, right? If this step was not there, let us say, if this step was not there, then in the sense, if there is no into 10, then there is no concept, no need to use PCA. So first what we do is, we will run the program as it is, then we will remove certain things and we will see what happens. Okay, without more number of dimensions, how the elbow method works, by using PCA, how elbow method works and shows the finite number of clusters, right? So right now we are using PCA, we are calling PCA class, and we are passing the number of components to be 2, and we are saying that out of 40, only 2 components are enough to capture the entire variation in the data. So n components is equal to 2, and we are fitting the PCA method, that is fit underscore transform, which transforms the data from original dimension space to transform dimension space with only 2 principal components, right? Now, as you know from the earlier demonstration, how to form clusters, right? How to fit the with the help of k-means algorithm, and we are plotting those clusters, right? And now what we are doing is, we are predicting on the uh, scaled data. We are predicting on the scaled data how the clusters are actually formed. So now, in order to run this, we have to see how many clusters are finally formed. Just run this code. So RAM and disk is getting initialized. Now the program runs. Now you see the elbow method for optimal k value. We have found to be 3 in the morning discussion. So we treat that at k value equal to 3, the elbow has bent actually. So, but this, sir, sir, now 97, sir. Professor 97. So as I told you, for some of the problems, seeing the bent in the elbow is not that easy, right? There is no clear bent in this particular line plot to safely say that the k value is finalized to be 3, right? But here we consider that this is the bent in the elbow on the basis of uh, s- uh, SSC value decreasing to drastically decreasing, right? SSC value is drastically decreasing from 800 to some around 680 or 600 and 690 change. So according to this drastic decrease in SSC, we treat that we finalize the k value to be 3, right? And we form clusters here, right? This is the transformed space with the help of principal components. This is the transformed space, and we are visualizing this data. Okay, any doubts here? Any doubts? Elbow method. Yes, I'll let you know. Sir, 100 members వచ్చాయి. 100 అయ్యారు ఇప్పుడు. Yes. So elbow method, you want to have clarity, right? Or just you're recalling that it is elbow method. Okay, fine. Okay. So I think you have got this understanding. Now what I will do is I simply edit this code by removing certain things, right? I don't want to see the don't want to work with the PCA as of now, so I simply edit these lines, let us say. So now this code is to be modified, what you say, slightly. Why? Because we are not passing any PCA points, right? Rather, we are passing only what you say, um, stand data scaled points, right? Data scaled points. So that's why we are what you say, we are not using any PCA here. So in the first first scene program, so we have seen the plot, right? So in terms of two groups, right? So we can use that here instead of seeing the plot like this, right? So what I will do is I will simply skip all these things to just see how the code responds, right? So hash, right? And based on the elbow curve, choose an optimal value is 3, number of clusters, found predictions, right? Data with clusters, right? And fine, I'll just run this code. It simply shows the elbow method, and at that point also we see the k value to be 3. We see the k value to be 3, and we will keep this file aside as of now, and we will plot the data, right, for 3 clusters once we see the remaining programs. Okay. Right now, we will once again open a new notebook, and we will upload another program for hierarchical clustering. File, upload notebook, hierarchical clustering. So this is hierarchical clustering code for the component similarity analysis of product design. So the component similarity analysis can be done visually also. Once we see this, we will see that program also, right? By using images. See here. Here we are importing agglomerative clustering class, right? Here we are importing agglomerative clustering class to perform agglomerative clustering, and we are saying that we would like to show a dendrogram, and we also would like to specify what kind of linkage. Is it a minimum linkage, maximum linkage, or let us say single linkage or complete linkage, right? For that, we are uh, importing those two things, submodules, from hierarchy submodule, right? So fine. Here also what we are doing, we are generating a synthetic data set, and we are manipulating them by multiplying it into 10 times, right? Number of samples and number of features. And we are saving this file, right? I will show you how the data looks like, right? I think I have shared this CSV files with you people. You can also open at your end to see how data looks like, right? But for the sake of in the interest of the lab session, I will show the data, one of the CSV files, and how to see the data, plot the data, we'll see, right? Then we are converting the data into zeros and ones, and after that, what we are saying is we are calling the what you say uh, class method, which is agglomerative clustering constructor. We say in technical words, we say this is a constructor, and we are passing parameters like number of clusters, because here uh, there is no requirement to specify the number of clusters, right? So it is the task of the linkage method to generate the clusters finally, right? And the distance threshold that you have used is 2. So you can convert this to single also, right? First we run with word linkage, and then we'll convert into single, because morning we have discussed single link clustering. So we'll convert this word to single once we see these results, right? So then you are fitting agglomerative clustering to form clusters, hierarchical clusters, and then you are generating the linkage matrix. So the matrix that you have seen in the morning session, that what you say, similarity matrix you are defining here, and that similarity matrix you are using to generate what is called as dendrogram here, right? So here, and if you see here, these are your distance values at a particular specific distance. The merging has been occurred. So these are different distance values. The merging merge has been performed. Merge has been activated, right? Now, so what we are doing is we are also specifying the cluster assignments, and we are printing them also in the below, right? And what we are doing is we are creating a data frame to hold these component cluster labels, right? Component cluster labels, and we are also showing the value counts, cluster counts. So just we run this code. Our interest is to understand this particular dendrogram, right? So just run this code. Yes, we have got the dendrograms, right? Dendrogram image. So if you see this, uh, so here we have how many number of clusters? Just add the number of clusters here. 32 plus 26, 58 plus 11, 69 plus 9, 75 plus 24, 99, right? So I think around 100, there are 100 clusters here, but one cluster is missing actually. But there are 100 clusters here. So 14 clusters, cluster 14 is repeated 4 times. A cluster 8 is repeated 4 times, and so on. It is showing me cluster counts in the decreasing order, right? Now 4 times in the sense it has merged for 4 times, right? 8 has merged 4 times, like 4 has merged 4 times, right? Now these are the feature values. It has considered 5 features, and the corresponding feature values are shown here, right? Now, so if I convert this value linkage from what to single, what happens, you see, right? Now simply I'll run this. कभी कभी पूछ तो जाता है वही हम लोग बहुत देर जा रहे करें So there is only one cluster, right? By the name 0, right? Only one cluster by the name 0. So there are 100 mergings here, right? There are 100 mergings. So just you can count it. This is one merge, right? 1, 2, 3, 4, 5, 6. Like this, you can convert to find the merges. How many merges are there, right? So there are 100 merges here. So earlier we haven't seen 100, and but there are so many clusters. For them, the number of merges got distributed. So, but here, when I say single, automatically it formed a single cluster. As we have discussed in the morning session, it formed a single cluster with 100 merges. Right now, you can change this to complete also, as we have seen complete, the value complete, right? Just run this. So for complete clustering, you have this kind of dendrogram. And how many clusters are there? Uh, 1, 2, 3, 4, 5 clusters. I think there are only 5 clusters shown. Yes, there are 5 clusters, and those 5 clusters are shown here with their merging counts, right? Any doubts? Simply we are changing the type of linkage, right? So based on this, you can have the different, we can have different dendrogram arrangement. Now let us say the distance threshold is not has been increased from 2 to 5, let us say. Right now what happens, we'll see, right? So how many clusters are there finally? 3 clusters. We have only 3 clusters. So there are 56 merges in the first cluster, 30 merges in the second cluster, and in the sense 30 clusters in the first 30 merges in the first cluster, 56 in the second cluster, and 14 in the third cluster, right? This is 56, 60, 70 plus 30, 100, right? So there are 100 merges altogether. Any doubts here? Now what is understood here? Now when you increase the distance threshold, the number of clusters formed got reduced in complete linkage clustering, right? Now is this true across other linkages also? We will check here. So this is single. Now you will run this single here. However, the point that we need to observe in single is whatever might be your distance, so it forms only single cluster, right? This is the crucial observation one need to have. So for single linkage clustering, you will at any point in time you will have only one cluster finally, right? So then I can convert this to word once again. So if you run this, so earlier, if, with the distance threshold 2, you have so many number of clusters generated, but now you see very less number of clusters, right? 9 clusters, 10 clusters have only generated. It has generated only 10 clusters, right? So you should understand that uh, when the distance is increasing, the the proximity values will now differ, because uh, the distance is a crucial factor between the points present in those clusters. The distance between those points is a crucial factor, right? So accordingly, if the distance is high, then what happens is the point moving from one cluster to other cluster gets reduced. So there is no point of generating new clusters altogether. So that's why you will see only fixed number of or less number of clusters finally forming. Any doubts? Right now, what I will do is, now I will quickly open what you see, component similarity notebook for image, by selecting the images. How do you find out the similarity between two components, right? So by using images. Now what I have already uploaded images, and the 1 minute I need to close certain sessions because too many sessions it is showing me. So hierarchy clustering, fine. So now it is possible to work with this. Connect. Morning, in the morning session, sorry, in the afternoon session, before beginning, before the start of this lab, uh, I have shared you two image names, right? These are the two image names, per space gear.jpg and helical gear.jpg. In helical gear, there is no space, right? So these two image files, we need to upload into our mounted Google Drive, right? So what we are doing is we are simply mounting our Google Drive here. First, I think my drive has got attached, right? So yes, it has attached, right? Now what we are doing is we are uploading those two images to the drive. I I doubt those images are already existing in my drive, but if they are not present, I will upload, right? SPUR FGH. So I don't think those are here images, but I will upload now, right? Fine. Now, so to upload that, what I'm doing is I'm clicking on this upload button and I'm selecting those images. So one, and Spurgear image, this one. Right. The important point here is the height and width of those two images must be same, right? If those, if these two properties, if these two dimensions are not matched for the image, then the program throws an error saying that the dimensions are mismatching, so that you need to once again go back and check and modify the dimensions in such a way that both the images follow same height and width, right? Now what I need to check whether these files have been uploaded or not. Yes, I think they have uploaded. Right, we have seen, so see here helical gear is there, image, and we also have spur gear here, right? So both the things have got uploaded, both the images. Now in this program calculates what is called a structural similarity index measure, structural similarity index value, and it has three values. uh, Plus one says both the images are 100% similar. Zero says there is no similarity between the images, and minus one, if the similarity index returns minus one value, then it says they are totally oppositely correlated. There is no they are anti similar, they are unsimilar, right? They are unsimilar, right? Now, so if you see, this program supports the three extensions, file extensions. If the images are in .jpg, or if it is in .png or .jpeg also, this program takes into consideration those images, and it calculates similarity. So it calculates similarity SSIM underscore index. Now if you see what is SSIM underscore index, so there is a definition called SSIM calculate, right? So what it is returning, it is simply returning image SSIM of image 1 comma image 2. So simply it is calling the method SSIM method, which we have already imported as a structural similarity function. So just by calling the predefined function, it will simply return the index value, SSIM value, in similarity index value. But in order to return this value, it should what it should do is it should compare the images, right? It should compare the images, and it should calculate the SSIM, right? So now how this happens, right? So where is this particularly images are present? Specify the folder. Now instead of uh, making them available individually, better you create a folder and specify that path. In this you have two images, spur gear and helical gear. So instead of supplying them individually, you supply as a folder path, right? Now what you see is copy this path and paste it here, right? It checks the the comparison of these two images happens uh, in terms of what is a pixel image to pixel image and the features present in that pixel image, right? Accordingly what it does is it finally what is a counts and transforms that into a value that ranges in between 0 to 1. So so now you see I have posted the images into the folder, upload the image into this folder, and this particular folder path we are using, and we are locating these images, right? See here, these images have been read from this path, and we are using those images to calculate the similarity, right? We are visualizing that similarity here, similarity results, right? So now just run this code. So the similarity between spur gear and helical gear is 0.429 value. So it is not 0, rather it is greater than 0, and it is moving towards 0.5, or let us say it is moving towards 1. But the value is less than 0.5. It means these two gears are actually similar, because it has got some value, return value like 0.429. That means these two gear images are actually similar in nature, right? So but these two gears, if the based on the value, are not highly similar as specified from this image. These two gears are not highly similar, but they are similar in different constructs, in the form of different constructs like teeth, gear teeth, what you say, gear teeth similarity, or in terms of edges of the what you say blank, right? And so on. Accordingly, these two gears are the surface finish of the teeth, gear teeth. So based on that, it might have calculated the similarity, and those all those things are nothing but the image features. For this program, all those things are image features. So the internally what is happening is the image features are getting compared here, and finally it has calculated the value and showing this value, right? So 0.429. So any doubts here? So any doubts, participants? So the same component similarity analysis we have done using appearance matching and we have also done using hierarchical clustering, right? Now, now, if you just want to see that image, I will simply show you that image, right? 1 minute. You share multiple and share one participant. Okay. So new share now. 1 minute before sharing this, I would like to share this image, right? So please let me know you are not seeing this image, but still, I will show you this image. 1 minute. New share. Right. I think participants are able to see these gears, right?
Yes, sir. Yes, sir.
Uh,
We are able to see this.
yes, in this
Now
image,
all types of gears we are able to
gears,
see.
right? You see, the first one is per gear and helical gear. Now I have made the similarity analysis based on this appearance matching of these two gears. Right now, you see the diameter of this particular, let us say, of this particular blank is some x, and the diameter of this particular blank is y. So the diameter wise both are now different, and the what is a teeth of the gear in terms of length both are differing in these two images, right? In these two images, the teeth of the gears are differing length in terms of its length, and the way the gears are oriented, right? After say what you say manufacturing, the surface finish of these particular gears is different from the surface finish of this particular gear, right? So the as the blank itself is different, obviously we when these two gears are compared, right, it shows a less similarity only. But if the helical gear is also is also manufactured with the help of similar kind of blank, then it might have shown a better value, right? So as the blanks are different, so is the SSIM value, right? These things are image features considered by the program. Any doubts here?
Sir, what is the advantage you will get with comparing these two, sir?
When you are saying component similarity, what you say while you are doing through conventional mechanical engineering manufacturing, when you want to do component similarity, what are the things that you will see in order to decide that these two gears are similar? Yes. Now,
Not able to follow, sir. What is the advantage of doing all this
I I
exercise?
I, I will tell you. I will tell you. What my doubt is, in conventional gear manufacturing, if you want to find out whether two gears are similar or not, what is the thing that you do? Yes, sir.
Application of spur gear is different from the helical gear.
Hmm.
Uh, Definitely, this I don't know, sir. What is the use of finding the similarity? That's why I'm asking, sir.
Yes, sir. If you when you find the similarity, component similarity, uh, in what you say in the product design, right? So you can actually reuse certain aspects of the what you say components when you compare two products while designing. Understood? So you can reuse the features. You can reuse certain features, right? So it could be the properties of the teeth that can be reused while you are trying to manufacture more of the helical gear instead of spur gear, right? As you are comparing these two gears, and you are able to understand that these two gears are similar, right? So in such sense, if at all any requirement is there with helical gear, and let us say you don't want to work with spur gear, and but the project is asking you to work with only spur gear, right? So like it is, as it is similar, you can reuse certain components in helical gear to, let us say, to use it as in some situations as spur gear, if I am not wrong. Can you replace spur gear with
Uh,
the helical gear at any location?
no, no, sir, because spur gear teeth is they are straight in nature, and then whereas
Helical
helical
gear.
gear they are inclined.
Okay,
So
these are
completely the application of spur gear is different from the helical gear.
fine, but these are structurally they are seem to be similar, right? We are only dealing with the structural
Structurally,
aspect.
they seem to be similar.
That's what we are calculating. What is called as SSIM here, right? Structural similarity index measure. We are trying to find out these two gears are whether they are structurally similar. But if you see in this diagram, structurally the rack gear is somewhat structurally similar with the helical gear in this particular diagram, in this image. Are you understanding my point?
Yes,
So
yes, sir. Yes, sir.
for that reason, uh, just to know whether these two are structurally similar or not, we would like to come up with a conclusion and say that these two gears are structurally similar, and uh, yes, so similar gears are there, we can actually conclude, let us say. And also when you are comparing two structures, right, you not only compare the what you say, outer features, but also see the other features, like, right, we see in you are saying in helical gear the teeth is somewhat different, right? But in in the rack part of the in the rack and pinion, in the rack part of the gear, the teeth is straight, right? Gear teeth is straight
Uh,
in this
Rack
image.
is a straight line, sir, and
Okay,
pinion
pinion.
is
Okay,
circular.
okay. Pinion
But both the teeth are straight only.
straight. Okay, fine. Yes, sir. In this diagram, I'm saying.
Hmm.
In this diagram, I'm saying
Helical gear, they are inclined, sir.
inclined,
Teeth are
inclined.
inclined.
Fine. So structural wise, whether the gears are similar or not, we are able to come to a conclusion. Any doubts, sir?
Sir, we will get that conclusion, but with that conclusion, what is the further we can do with that? That's what my question
That
is.
we need to sit and finalize, because I have done till this point. I need
Okay,
to still
okay,
check
thank you.
what will happen. What is the essence of comparison, comparing what you say, these two gears, right? That we need to
Yes, sir.
go ahead and come get back to you. I will let you know what is the conclusion for your answer for your question. Okay,
Okay, okay, sir. Thank you, sir.
I
Thank
will
you, sir.
give you the answer in the group by today evening. Okay,
Yes, sir.
so
Thank you, sir.
okay, fine. Thank you. Now, now we will finally we will see the PCA problem. See, we will upload the PCA, manage sessions, file, open or upload notebook, generate PCA, right? So PCA, we have already seen in the k-means itself, right? Now what we are doing is, we are calling PCA class, and we are supplying the number of components, right? and and we are converting the entire data into zeros and ones by using standard scalar class. And now what we are doing is, we would like to find out the variance ratio in the generated components, right? Explainable variance from the generated principal components. So we would like to find out which particular principal component can be utilized to explain variance in of the data, right? In the majority wise, that means major variance can be explained through first principal component as per the morning discussion, right? So whether that is possible or not, we are able to understand now with the help of this. Now you see here the principal components are shown as 2 because we have considered the number of components to be 2, right? And now the first principal component has variance highest, better explained variance ratio as compared to second principal component, right? It is somewhat above, more just to be above 0.25, just greater than 0.25 the second principal component, whereas the first principal component is almost moving towards 0.5, right? It is around 0.75. So in between these two, as theory said, the first principal component, you see it is 0.2809 first principal component variance and ratio, and second principal component 0.26. So yes, so these two, we are utilizing these two components, and we are plotting the transformed axis, right? Transformed axis. So now what we would like to do is, now I will make you introduce to the concept of GeoGebra here. 1 minute. So GeoGebra. So GeoGebra is a site which you use for doing various mathematical calculations, and you can also do plot the graphs, right? So what we are doing is, we are forming an expression here. So this expression, we would like to see in the form of a vector. So 1 minute, how the vector can be formed, I will show you. Gebra.org/m, right? So I think the same website is here now. Graphing input tools, slider, best fit line, points, extremum roots, lines, vector points, right? So we have vectors here, you see. We select starting point and then end point. So specify the starting point to be this one, and the end point is here, right? So we have a vector generated here, right? So you see, this is one point, and another vector moving in this direction, right? So these vectors, I can also look, get the, how to say, 1 minute. I think I can delete this vector, right? 1 minute. uh, Show trace animation settings, I can delete it. Actually, there is an option, no? Okay, we have this, the undo option, right? Okay, I can also find the angle between the two vectors, actually. mm, Algebra, show head, visual style, intersect. Mm, Vector from point. vectors ray line. 1 minute. Here there are settings. You should show me the angle also. 1 minute. 3D algebra. So the angle between the points. So I can type here. So that is 1 minute. So this is once again. Where is the point to note? So we are about to end this session. 1 minute. Before that, I would like to see how to specify the angle, right? Angle between the points B comma C. Or let us say if I draw another vector, let us say from here, let us say why it is not showing me the you should able to draw a vector, right? Okay, just to know whether what is the angle between the points B comma C. So now just I click enter. What it is showing me? It is showing me some error. Please check your input. 1 minute, please. So I would like to find the angle between two ABC, right? So angle between A comma B comma C with BCA, let us say BC B comma C comma A. It should show up the angle, right? Unknown command. Fine. You should show me some value. Let us say alpha A equal to, right? Then it should show up the value, right? Set symbols. Some x equal to, fine. See this one here, x equal to, should give me the angle, right? You should specify the angle. Somewhat some you're able to see, we should able to get that angle, right? But still you see we have defined the points 4 comma 3, also defined the point 6 comma 3, and we have created a vector BC whose value is 2 comma 0, right? But it is not showing me the angle. I will see this. I strongly suggest all the participants to use this tool, right? To you understand about the vectors, concepts of vectors, and so you there is a angle method, but right, fine. If you have any doubts, you can ping me, and today afternoon I will. By today evening, I will answer the question. One of the participants has raised the question: what is the essence of comparing two gears? Right? I will get back to that participant by giving the answer. Fine. Right. Thank you.
Participants, still you are having any doubts, you can ask about.
Teresa, can we make the angle of AC?
Yes, participant. What is the doubt that you have?
Sir, what is the use of the similarity index, sir? We are comparing two entities.
Right.
Then we are saying some number, whether they are similar or not, how much similar you are saying. So
Yes.
with that, what we can do with that one?
So in image processing or in computer vision, what happens is, let us say, we want to classify two images like cats and dogs. For simply a simple example, I'm telling you, if you want to classify two images like cats and dogs, and if you want to finalize, or if you want to say that the given two images, whether it is a dog or not a dog. So there is a difference, please. The first one is, you are simply classifying, you are simply drawing a line saying that these images belong to label cat and these images belong to label dog, right? In the second question, in the second thing, what I am saying is, I would like to, I am showing two images to the camera. The first image is purely the dog image, and second image is a cake on which stuffing is made, right? On which stuffing is made in such a way that it looks similarly like a dog, right? So now, the machine learning algorithm or deep learning algorithm should be in a position to clearly say that this is a the image, this is a dog image, and this is not a dog image. Understood?
Yeah, yeah. Okay, sir.
So
Follow.
for that reason, we are comparing the images in terms of its structures.
Okay, sir.
So here also, in this your doubt also, we can actually differentiate set of helical
Yes,
gears with a set of spur gears.
okay, sir.
So right, but here we are trying to clearly say that these two are similar,
Okay, sir.
but they are not same.
Hmm.
Right? If I simply substitute, instead of using helical gear image there, if I simply use same
Spur
spur gear by what is a what is a creating a duplicate entity of spur gear, the same image, if I'm copying second time for the first time, I have two copies, right?
Yes, sir.
Now I upload the second copy into my drive and I will compare these two spur gears,
Yes,
and
sir.
it will return me the value 1,
One.
right?
Yes, sir.
But I not required. I would like to find out whether these two are similar or not.
Okay, sir. Okay.
So
Understood,
that,
sir.
okay,
Okay,
sir.
thank you, sir.
Okay, sir. Okay. Thank you. So any doubts, participants?
Still any doubts, some participants? You can ask.
Sir, will you inform about tomorrow's and day after tomorrow's schedule?
Yes, sir. Already for tomorrow morning, I have posted in the group, sir. The details I have posted in the group already, in the FDP group.
Okay, okay,
Yes, sir. Yes, sir. We
Tomorrow.
received the information.
okay, okay. Thank you, participants. We will once again meet in tomorrow's afternoon session, lab session, and also we'll also
Saturday afternoon.
Saturday afternoon also in lab sessions we will meet. Okay. Thank you very much.
Okay, okay, Santosh, sir. Thank you
Okay,
very
sir.
much.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you,
Thank
sir.
you. Thank you.